can start now. Okay, so it's a pleasure to have Anatoli Polkovnikov today. Anatoli, professor at BU, Boston University, did really amazing work on non-equilibrium physics, and I think many of us are feeding off of his ideas. And today he's going to tell us how to really do driving, how to do driving, non-adiabatic driving. Try to do it in a precise way in a many-body system. Is that right?
Yes. Yes.
Great. Okay.
Okay. Well,
okay. Thanks, Anatoli.
Thanks for inviting me. Hope we will resume soon, like in-person meetings. At least I'm reasonably optimistic. So yeah, I will. Yeah, I understood that. Oh, did I mute myself?
I muted you by mistake. Sorry about that.
So I decided to give like roughly an overview talk about sort of this topic. I will probably hopefully connect it to some questions we like to understand, like annealing, dissipation, and so on. But of course I won't cover all the topics. Maybe in the end I will give sort of summary what else can be done. So I was very fortunate to have like many collaborators. Some of them students, many of them finished already, some continue. So let me just say that we started this work and basically kept collaborations until now with Dries Selfs, who is now a professor at NYU. So almost all I'm going to say was done in collaboration with him. And also a lot of like, some key ideas I'm going to present were developed by Peter Klaes, who is spent 1 year as a postdoc in BU, so he's finishing his postdoc at Cambridge, mostly working with Austin Lamacraft, and he's moving to Dresden. But there are other people involved as well, maybe I mention when I talk about specific things. So I'll start slowly. I'll try to show some equations. I apologize if it seems technical, hopefully they're not long, but I want to give sort of some ideas how things work, and then I will show hopefully pictures and explain the results. So let me start from, and I apologize. So this is work which I was sort of involved for 6 years. So some of you heard some of my talks, you probably recognize some of the slides, but I really updated the talk a lot. So there will be definitely new material for anyone. So let's just start from a very simple problem. And I'm going, by the way, to mix quantum and classical because lots of things actually are very similar in quantum and classical world. I guess classical systems are easier to develop intuition. Quantum systems actually in many senses are easier to develop formalism. So let's just imagine that we have, say, a particle in some moving potential. So we have a box which is presented by some potential, and say we move a box. And then we want to understand like how to solve the problem so this particle can move in one box. Well, and we know that, well, it's much easier not to work in the lab frame, but instead go to a moving frame where we just change the coordinate to relative coordinate of a particle with respect to, say, left of the box. And we all know that actually then we have to modify the Hamiltonian. So in a way, we got now a static box, so nothing moves there, but we got a new term, which is Galilean term. But yet the problem is much simpler. We don't need to worry about, say, moving boundary conditions or whatever. And by the way, from this, we also recover classical adiabatic theorem, right? We see that if box velocity is 0, x naught dot is 0, this term is not important. Hamiltonian is always static. So it's a nice way to see how adiabaticity works. So, and then actually, relatively recently, I would say 2003, it's 20 years, but well, given when all these things sort of well, classic Hamiltonian dynamics existed for probably 100 years already by that time. So relatively recently, there were ideas coming from two chemists, actually, Demirkplak and Rice in Chicago. And then independently, 6 years later, same ideas were developed by Michael Berry for quantum systems, but I will tell it's exactly the same as for classical systems. That actually, if we want to enforce adiabaticity without requiring zero velocity limit, we can actually add a counter term, right? So this term actually makes Hamiltonian time dependent, right? Because these terms are explicitly time independent in the moving frame. So the idea is that, well, let's just add it back. We just add counter term back, right? And in the moving frame, now our Hamiltonian is just completely static. So it means that no matter how fast we move the box, what's time dependence of x naught or whatever, our Hamiltonian is always static. So it means if we have a particle inside the box, we will not excite it. It will follow whatever equilibrium state it has. So for example, it can follow a ground state. Okay. So I'm not going to talk much about this, but let me just sort of say a couple of words that this is not something we usually realize in the lab because term linear NP is difficult. Well, maybe if a particle is charged, we can do it, but if it's neutral, how do we realize it? But what one can do like momentum shift, like we do in electromagnetism. It's another canonical transformation. And if we do it, we will get a Hamiltonian, which is extremely familiar to us, right? So when we shift the momentum, we'll get another Galilean term, but now with x instead of p, and there is a minus sign because, you know, x and p are the opposite. And then we recognize, well, this is something we know very well. We just need to introduce gravitational field proportional to acceleration. So in this sense, I did something trivial. Of course, Demirkplak and Rice and Berry developed things in general. It's not that they found sort of new answer to this simple problem. So there is one caveat, though, which will not be sort of important for you, but for me later, but I want to maybe still stress it. So this Hamiltonian has a shifted momentum of the particle. So it's actually this, if we want this Hamiltonian to work, we need to start and add at zero velocity, because then initial and final momentum is the same. And this is actually sort of these tricks I used a lot in quantum annealing and whatever. You just introduce maybe extra controls or whatever, which vanish at the boundaries. But anyway, this is really a subtlety, and I don't want to go there. So, and this is the picture actually we came up with this after some thinking. Well, I think this picture is stolen, but sort of we came up with these images. That which kind of shows that this counter-adiabatic protocol is not fine-tuned to this particular problem, at least to a good level of approximation we can implement in practice, right? So here is a waiter who implements counter-adiabatic protocol by tilting the tray. In this way, he can avoid these non-adiabatic transitions, which sort of lead to I don't know, spilled food or drink or whatever. Okay, so, well, this was all fine, but now let's try to see, can we find a general approach? So basically, we want to find some canonical transformation where Hamiltonian is time independent, right? Up to, I don't know, some rescaling, so trivial things, and then add a counter term. So first, well, what are the canonical transformations? Well, normally we know them from generating functions, but there is a much easier way to define them through, well, generator, or I will refer to later gauge potential. So if we have any continuous canonical transformation, then it can be written in sort of this way. So lambda is a parameter and a is arbitrary function. So it's almost like a Hamiltonian equation of motion up to a sign, and a is arbitrary function, but we know it preserves Poisson brackets. So this is the way to find the canonical transformation. So in some sense, finding continuous canonical transformations is like finding n. So if we do our Galilean shift, it's very easy to see that generator of the shift is momentum, of course, as it should be, right? Because if this a is equal to p, then dx d lambda is -1. as it should, and the PD lambda is 0 as it should. So, well, we all know in quantum mechanics, momentum generates translations, but it's actually a result coming from classical mechanics. And now if we ask what are the equations of motion, if we are in the moving frame, so our X definition of what we mean by canonical variable depends on lambda, which depends on t. This is moving frame, right? So then when we find derivative, there will be contribution due to, well, when lambda is constant, and then contribution due to velocity. Then I said, well, dx d lambda minus d dp. And you just recognize that you find this moving Hamiltonian in general. So before I said it's a Galilean transformation, but it's actually a general result. So lambda dot is the rate with which we change parameter, and a lambda is the generator of this canonical transformation. So if you do rotations, you will get angular velocity times angular momentum. Okay, so CD driving, we just need to, sorry, I jumped too fast. So when we do counter-diabatic driving, we just need to add this term back. So now we are facing two questions. So we want to realize counter-diabatic protocol, meaning we want to suppress dissipation, right? We want to change some parameters fast, and we want to avoid any transitions, right? So now we need to solve two problems. First, which canonical transformation makes Hamiltonian time independent in new coordinates, right? And second, how we can realize this term in the lab, right? And I'll try to maybe answer, mostly I'll focus on question one, and then in the end, I'll tell you about question two. So when we have a moving frame, we actually don't need any formula. We just look and see, right? It's obvious which canonical transformation we have to do. We just need to go to this moving frame. And then generator of this transformation is momentum, and then I'm getting CD Hamiltonian as I discussed. So it's like sort of one-line calculation. But suppose instead we say change nonlinearity in this potential, right? To change, say, magnetic field or whatever. So just take another simple example, but less trivial. So we have harmonic potential plus some extra term. And then we ask, wait, what is the canonical transformation which makes this Hamiltonian time independent? And that's actually a much harder question. So if you want to guess, I don't think you'll find an answer. At least it's difficult. Well, let me switch to quantum systems. I could actually continue with classical world, but actually quantum systems, I think intuition about formalism is sort of more developed for us, at least for me. So in quantum systems, we don't deal with X and P, we usually deal with quantum states, right? And there, moving frame is defined as time-dependent unitary transformation. So we basically go to a basis which depends on time. And then we know that in this basis, Hamiltonian will be addressed by unitary. So now it's really simple exercise that if we plug this into Schrödinger equation, we will get exactly the same Galilean term. So H will be H minus lambda dot A lambda, where A comes from differentiating this unitary. It's of course a well-known result. Maybe what is well-known, we can sort of, without changing the frames, we can just introduce moving derivative. It's like we take psi, we undo unitary, so we rotate the basis, differentiate it, and apply unitary back. So this is what moving derivative is in quantum mechanics. And then what we get is precisely this H minus VA term, right? So, but in quantum mechanics, we immediately know what it means to make Hamiltonian time independent. We just diagonalize it. Right. So, well, there are, of course, energies which can depend on time, but it's not affecting dynamics. This is just phases. So in some sense, we solved the problem, which I said is non-trivial in classical world. We solved it in one line in quantum world. So we know what it is. But then, of course, the question is moved, what is U? What is unitary which diagonalizes Hamiltonian? And in general, we don't know the answer. Right? So, but actually, we can move forward with this quantum analogy and just realize that diagonal matrix commutes with itself at any value of lambda, right? We change lambda, it's still diagonal matrix, two diagonal matrices always commute. So it actually means that we can equivalently say this condition that H tilde is diagonal is like commutative derivative of this H tilde, and H tilde is 0. So derivative of rotated Hamiltonian commutes with rotated Hamiltonian. And then derivative again is very easy to evaluate. We will get two contributions from unitary, and then what you will get is that, well, you will get, well, explicit derivative of d lambda h and commutator is a in h. So now we know what we mean by this A, which sort of diagonalizes or makes Hamiltonian time independent. We just sort of need to solve this equation. I just wanted to make a quick remark that adiabatic transformations extend the notion of symmetries in some sense, right? Because what are the symmetries? Symmetries are precisely rotations or canonical transformations which make Hamiltonian invariant. So if d lambda h is 0, so lambda is a fake parameter, right? I'm just asking, what is the family of transformations which leave Hamiltonian invariant? And these are precisely the symmetries. But here we have this extra source term. So if source term is non-zero, we extend the notion of symmetry. But now we immediately see what's the classical answer. Well, I put factors of h bar just to see or to emphasize that in the classical limit it goes to Poisson bracket. So at the end, if we want to solve first question, we just need to solve this equation. For this equation, right? And then we know which variables, if you want in classical language, make my Hamiltonian time independent. So let me come back to this example, this nonlinear potential. Then dh d lambda is x power 4, and then I need to find A such that this sort of Poisson bracket is 0. I'm not going to write explicitly what this equation is, it doesn't make sense, but I just want to highlight, Poisson bracket gives derivative on A is only a known thing, right? So it's a second order partial differential equation, and it looks completely harmless. But there is one caveat, and of course it works in all dimensions. I'm showing one-dimensional example, it doesn't matter. There's one caveat. It turns out like using different language but basically same object, like actually thinking about how one can generalize Berry phase to classical chaotic systems, Chris Yerzinski came up with a proof that in chaotic systems, this equation has no solution. Solution just doesn't exist. So what do we do with that? Well, first of all, yeah, I'm sort of contradicting myself. I just said in quantum system solution is trivial. So how we reconcile them? Well, it turns out that if you take chaotic systems, is a classical limit, h bar goes to 0, or thermodynamic limit, then from this whatever random matrix ideas like eigenstate stabilization hypothesis, it's very easy to prove that the norm of this gauge potential scales as exponent of the entropy. And we know entropy diverges either in classical limit or in thermodynamic limit. So it basically means that the solution is exponentially large. So formally it exists, but if we take Hilbert space to infinity for chaotic systems, it does not. So in this sense,
entropy of what? Sorry,
entropy of the system corresponding to this eigenstate. So if we have chaos, then each eigenstate is like thermal equilibrium, right?
But this is what I mean. Yeah. So
this is entropy of. So sorry, this is
a pure state.
Right. Oh, it should be a squared, by the way. So this is basically variance. Norm of this A is the variance of this gauge potential in an eigenstate. If we have chaotic systems, that eigenstates are like microcanonical ensembles. This is basically statement of eigenstate thermalization hypothesis or random matrix theory. And in this state, there is entropy, which is defined through density of states, exactly like basically inverse level spacing, if you want, in quantum mechanics. And this entropy diverges either in thermodynamic limit or in classical limit or in both, right? So, and well, basically this statement is not surprising because if you think, I'm just saying that if A exists, you can exactly follow eigenstates. But if my system is chaotic, I just shouldn't be able to do it, right? Because they should be exponentially fragile. I have random matrix, it's super fragile. You need exponentially tiny perturbation to break down all your eigenstates.
So, sorry, just technically. So, what you mean by this entropy is the density of states?
Yes. It's exactly thermodynamic entropy, the way we understand it. Right.
Okay.
Yeah, density of states.
I'm sorry, may I ask a question?
Yeah, sure.
So, I kind of see that this entropy is scaling either in the classical limit or in the thermodynamic limit, and that a classical system, a chaotic classical system, is in one of these limits, and therefore you're already in the regime in which this doesn't apply. But isn't there a way in which you could? So does the solution just not exist, or there is one that is just super hard to follow because of chaos?
Well, the point is that you cannot really follow it, because if you think about thermodynamic limit, large L, right? For any L, it exists. But if you add one side, then your solution is totally different. So there is no smooth function. It's sort of like a projection operator. Formally, it exists, but this is not smooth differentiable function of any parameters, right? That's why it's not, I mean, it's like projection on chaotic trajectory in classical system.
Mm-hmm.
And it's formally for any classical system, you can define it. Let's just start from a given point and follow it. But if you want to ask what's the function which projects to the chaotic trajectory, it doesn't exist, right? So there is no smooth differentiable function which solves this equation. So that's what
Thanks.
So what are the ways out? Well, first is like, I don't know, standard, if you want, it's route to integrable systems where we deal with classical systems. And indeed, there are actually many connections with integrable systems. Let's try to find situations when we can find the solution, right? So I'll just guide you some simple examples. And actually, there are quite non-trivial answers already at this level. For example, we need this object, right, this rotated derivative, to commute with h. So why don't we say it's some function of h, right? It's an ansatz. I'm not trying to prove that all solutions of this form. This is just an ansatz which clearly solves this equation, right? And then let me choose some potential. I switched to q here from x because it's actually a slide from some years ago. So I decided not to rewrite this equation. So q means x. So I have still particle in one-dimensional potential. And basically, I want to solve, for example, this. I say stop at the level. Well, identity is not really, well, I can always add identity. I stop at the level h. I don't consider h squared. So let's see what goes on. Now, if you stare a little bit on this equation, you just realize that the solution has to be odd function of momentum. Again, quantum mechanically, it's sort of trivial. H is real. The way it's written, there is no magnetic field. There's extra I here, so A has to be imaginary. Otherwise, I won't solve this equation, right? And imaginary means odd in P. If you write Poisson brackets, you write derivatives, you just recognize immediately that this is, say, even function of P. In order to make this even, it has to be odd in P. So we can try an ansatz. How about it's P times some function of Q plus P cubed. In principle, it could be also function of Q plus and so on. So this is an ansatz. Then we plug it in and ask, what are the consistency conditions? It's a very simple exercise. I'm not going to guide you through it, but it's like really you spend, 10, 15 minutes and you find all the answers. So first we can say, well, let's just forget about cubic term. Let's just try linear potential. And then actually, remember I said it's generator of canonical transformations. So if f is constant, these are translations because it's P. If f is q, it's actually dilations. I didn't tell you, it's by system. Actually, this problem was also solved in 2014 by Defner, Yerzinski, and Del Campo. And they found that the only solution in this case are translations and dilations. There is nothing else. And the potential which can sort of satisfy this, so for which we can write this A and solve this equation, is really involves translations, which I showed before, but you can also squeeze it. So if you just, instead of moving the potential, the box, you're squeezing the box, you can still find exactly. Now we can ask, what if we add P cube? And then it takes an extra few minutes and actually recover something interesting. This V has to satisfy KdV equation. And some of you are probably experts in integrable systems. This is exactly what's inverse, whatever scattering methods give you. So if you basically want to change potential in a way that there is exact counter-diabatic term, this potential should satisfy this equation. And solutions of these equations are solitons and breezers. So this is like interesting connection between quantum and classical work. And by the way, dispersion is given by quantum mechanics. So if you are classical, h bar is 0, you have dispersionless KdV equation singular. So quantum mechanics really gives us scale and removes singularity, right? So if you want to find basically an annealing protocol for quantum problem, we should satisfy classical KdV equation.
What do you refer to as this? I got confused, but what do you call the consistency condition?
Well, basically, I'm trying to solve this equation, right? So this is what I'm trying to do. And then you see here, I have function of, which is linear, zeros order in P, basically function of Q and P squared, right? So here I will also generate terms which are P and P squared. With this ansatz, it's very easy to see, like Poisson bracket, for example, will be dA, dP, dH, dx. And if you do it correctly, dA, dP will be, say, P squared, dH, dx will be dV, dQ, right? So it's P squared, right? So you basically want now coefficients of functions in front of P power 0 and in front of P squared to vanish, right? Because you want left-hand side to be right-hand side. And you get two equations. And it turns out that they're inconsistent unless V satisfies extra constraints. And well, you just have to do, actually did this exercise, but we didn't publish because we found the paper we actually did it the same year. So there was a paper already, so we gave up. But I did this exercise, it's sort of very simple. So you just see that V has to satisfy consistency conditions, and this is the consistency condition. Otherwise, these two equations are incompatible. And this actually, what we're getting is part of magic, which I sort of don't understand. I was too lazy to show you particles which are moving, but let's imagine that these are particles and these are velocities. And this sort of lines represent solution of KdV equation. This is one soliton, these are two solitons. I stole it from some site. And so what I'm saying that if we are moving these potentials, these bumps, arbitrarily fast, these particles are not excited. So if I want to use colloquial language, I just took a picture from a movie being there. It's like, I think the final, basically the ending of this movie shows sort of this when this guy walks on the lake. And there are two surprises. First of all, he doesn't go down. It's one surprise. But the second surprise, there are no ripples. So, and what I'm saying, it's actually, this could be real for particles. We can have many fermions, like full Fermi C and so on. This is non-interacting problem, of course, but it could be many particle problem. We will not create a single ripple. So it completely contradicts our tuition, but there is a caveat. We need to introduce this counter-diabatic term, which is proportional to P cube. So, and this brings me sort of naturally to a second question, which I'll answer a bit later, how we can realize this P cube in the lab. So if we could, we actually will be able to move potentials like tweezers, if you want, without exciting a ripple. So I guess it's counterintuitive, at least for me, because I have no idea what this term is doing to my dynamics. It's unusual, right? And for those that way, by the way, who know integrability, which I don't, this is Lax operator. So these things are very closely, very closely related to integrability. Okay, so now let me ask a little bit more complicated question. What if we don't want to fine-tune the potential? We basically have Hamiltonian as is. And I just told you, there is no exact solution, but we know very often in physics, we don't have exact solutions, but we have approximate solutions. Or not only in physics, in optimization problems. If you have like very hard problem, it's very hard to find exact solution, but there are many good solutions, right? So, and then there is like extra, almost final part of math I want to impose on you, is that this equation which I'm trying to solve is actually equivalent to a minimization problem. And you can sort of almost see it, how it works, because if I apply this A, it cannot affect diagonal elements of this d lambda H in the basis of H, because commutator is not really affecting it, but it removes off diagonal. So it actually means that if I compute G squared, like square of this object, then best A will only keep diagonal elements and nothing else. And then you just realize, well, if I minimize G squared, I find the solution. Now you can just minimize with respect to any positive measure which commutes with H. For example, it's a function of H. It's just some mathematical statement. So we can choose this measure to be ground state wave function. Well, of course, it commutes with eigenstate. We can choose it to be identity. Then actually, you have lots of advantages. You have weak theorem. You have you can do things analytically very efficiently and so on. You can use it as a Gibbs distribution. It also commutes with H. Or you can use it as a microcanonical ensemble. Or you can just come up with any other measure. So basically, as long as this measure is sort of non-zero on different eigenstates, you always have unique solution. Well, say if you have finite Hilbert space. If this measure does not have any weight on some states, like you only loop into ground state, it gives you actually, well, it gives you a solution which say doesn't excite ground state, right? So if you're interested in quantum annealing, you, for example, might not care whether you excite from state number 10 to state number 11. You only care that you don't excite from state number 0 to state any other state. Anyway, so there are some caveats, but let's say it's an arbitrary measure.
Anatoly, I'm just trying to make this a bit more precise because I get confused. You're saying that if I take this measure and are you saying that I could choose any P that you know is not an identity? Yes. Or?
Yes, for exact solution, it doesn't matter. But if you find approximate solutions, of course, you bias your solution towards your desired energies. Like if you're interested, so for example, you're interested only in the ground state, like in quantum annealing, then you can choose the measure, which is just ground state. And then your solution might not do very well at high energies, but you don't care. But for the ground state, it will do very well. So your approximation, it's like sort of, if you want, it's like with variational ansatz in thermodynamics, right? You can find best free energy variation, right?
But is it easier to compute? I mean, it looks like the easiest thing to compute this for would be to plug identity.
Exactly. But not always work. Yes. So, and we did for spin systems, that's exactly what we are doing. And I will comment. So amazingly well, the solutions work very well for ground states. And this is, for me, still a big mistake. But yes, for identity, it's much easier because you don't need to diagonalize Hamiltonian, right? Finding trace of G squared for any local Hamiltonian is a trivial thing. Because if you want trace of sigma squared is 1, trace of 2, whatever, trace of sigma is 0. So you don't need to diagonalize anything. And most of the examples I'm going to show, they correspond to P of H identity. But sometimes this measure doesn't work.
Okay, thank you.
So yeah, and for classical systems, so for classical systems, it's again same thing. I have same G squared, but now instead of trace, I have phase space integral. And again, with identity, it's easy. If I think about spins, I integrate over angles. And again, it's very easy. Integral of sine squared is whatever, 1/3. Integral of sine is 0. So you just get slightly different coefficients, but exactly the same thing. So we can now, because it's minimization problem, we can devise variational procedure. So we don't know, or cannot find in principle exact solution, but let's try to find best possible solution. So how we proceed? We choose variational ansatz, like for example, based on say proximity to some integrable case or our intuition or intuition of our friend or what we can realize in the lab. So we could come with some variational ansatz, compute this object, it's trivial, right? Once we have this A, which is say local computing commutator is trivial, minimize, and as Nathaniel pointed, like if we use identity measure, it's like trivial quadratic problem, and then run the CD protocol. So, but actually, just want to highlight one result, which will be also important a bit later, which actually Peter Kleis found, that actually there is a smart variational ansatz. It turns out that, I didn't talk about this, but generator of adiabatic transformations is related to what's known now as operator growth in quantum mechanics. So it can be expressed as time integral. It's like I'm playing with some lemon representations and so on. I really don't have time for this, but there is nothing complicated there. So, and if this is Heisenberg representation of my d lambda h. And actually in classical systems, that's exactly what Jaroszynski got. So here d lambda h of t is just my it's a function of t, like standard classical function. Anyway, so, and then if we do short time expansion, we will get exactly this odd commutators. So we get infinite series. And Peter thought, okay, we have infinite series, we don't know how to compute it, but let's use these terms as variational ansatz. And it turns out that this is extremely good, extremely powerful variational ansatz. So once we applied it, we were surprised. And you have very few variational coefficients in this way. So let me now move to examples. And I'll start from this nonlinear oscillator. It was actually done by an undergraduate student, Nick, who is now finishing. So let's start from one oscillator. So we want to turn on nonlinearity, right? And then we are aiming at the end to Fermi-Pasta-Ulam problem where there are many oscillators. So there we cannot use really quantum measures like fidelity and so on. So for one oscillator, he solved this problem quantum mechanically. Classically, results are nearly the same. So I'll just show classical results. So for classical systems, good measure of non-adiabaticity is energy variance, right? So if we initialize our particle in some microcanonical ensemble, that's analog of quantum stationary state, then if we do things reversibly, it will remain in microcanonical ensemble, right? If we do them irreversibly, we will have energy spread. So, and this is a very good measure, like figure of merit, how we check our protocol. So if we have fast evolution, of course, we expect large spread. If the particle happens to be in the center, it doesn't care what we do with potential. If it's near the edge, we actually increase its energy a lot, right? So if we have slow evolution, all particles feel exactly the same forces, and therefore we do exact same thing to all of them. And this is simulation. What happens with energy variance as a function of duration of the protocol? It's log 10 scale, so don't worry that it looks narrow. So these are long times, these are short times. So long times energy variance is basically 0, short times it's finite number. Now we do CD driving. So we go through this exercise and do this commutator expansion. And interestingly, in the first order, we find x cubed p term. So that's the leading term we want to apply. And we use variational procedure to optimize this coefficient. And the second order, we again get p cube x term. So the same which I showed in this whatever KDV thing appeared. And then we just see what happens with energy variance if I apply this protocol. It's already, of course, numerical problem. Even it's one-dimensional, it's difficult, sort of nonlinear system. And then we see that, well, first order actually gives some improvements. And actually, if you look into quantum fidelity, it gives 0 improvement. So for energy variance, it works better. For fidelity, it will go by sort of 5% down. But the moment we apply this magic XPQ term, we get some fantastic results. So variance goes by like 4 orders of magnitude, right? Almost 4 orders. So it's almost 0, right? So this P cube term, even though there is no KDV, well, it's not chaotic problem, but still exact solution is an infinite series of all momenta involved, so it's very complicated. So, but this approximate solution does an amazing thing. And now if I do this Fermi-Pasta-Ulam problem, where we have like, 50 oscillators with nonlinearity, and we do the same thing, we turn on this nonlinearity, well, we get slightly worse performance, but still like spectacular. We do the same commutator expansion, we also get these P cube terms. Now they are not completely local, they are nearest and next nearest neighbors, but anyway, so we get what we get. We apply and we get same similarity story. We get dramatic improvement. So it's, I'll show in the next. So it's basically we are throwing stone into the water and don't create a ripple, at least visible ripple. So it works amazingly well. But again, how do we implement this? How do we implement these terms like xi, pj cube, or things like that? Well, now I don't want to show just my works. This overview, I stole some slides from works of others. So this is work done in Innsbruck group. Now it's quantum annealing. So it's some circuit which Lerner, Hauck, and Zoller developed just to solve NP hard problems. I really know almost nothing about what exactly they're doing. They somehow use 4-spin interactions to convert, I don't know, 1D geometry to 2D geometry, sorry, 2D geometry local to 1D geometry non-local. So that's all I know about it. Anyway, so it's a difficult Hamiltonian to do annealing. So that's the thing which is important for me.
But that is just Anatoly, this four-spin interaction is local or
yeah, this is local.
Local in space, or
yeah, this is local in space. But the interesting thing that they have like architecture like a triangle, so expanding, and it turns out that somehow their spins, computational spins, are actually encoded in this sigma z's, but not directly. So they encoded it some plaquettes, and it turns out that effective model for computational spins becomes non-local. So they come up with this trick, and I heard it talk beautiful, but I forgot the details.
But physical spins, the interaction between physical spins
is local, yeah. So that's the idea. They have local 2D model and map in this way to non-local circuit, which could be arbitrary non-local. So any, like, you know, NP-hard problem. So, and then they did this variational implementation. So here the leading order term will be sigma y's. It also should be imaginary. And then variationally they can find these magnetic fields, which know about interactions and so on. It's again, we actually did it for different Hamiltonian as well. It's a very simple exercise. Quadratic minimization problem, don't need to, and it uses infinite temperature minimization. It's really simple. So basically they apply this counter term and see how it works. So here they show annealing. Here it's basically energy above ground state. They show similar results. So let me focus on annealing. So if they do just standard annealing, again, when velocity of the protocol is high, so time of the protocol is small, they have very small fidelity, and then this counter adiabatic improves it. I mean, not to 1, it's approximate, but it improves it. So, and actually there are many groups which, like, well, at least few groups which implemented similar things, and they also saw improvement. In some problems it was better, in some problems worse. Then one can ask, like, can we go beyond single spin, go to 2-spin? Then it turns out that our CD term will contain 3-spin terms. And then again, the question, how do we implement them? So let me show one more example. It's, I even didn't know how to call it. I call it, thought that maybe I'll call it theory mental realization on IBM simulator. Why? Well, you see, if we take our, say, Apple computer and do simulation there, we call it theory, right? If we take experimental system, like some material, and do some protocol, we call it experiment. Well, but this is the IBM quantum simulator. So I don't know, should we call it computer or experimental device? And I guess there is slow transition from one to another. I don't know whether it will happen in our lifetimes or ever, but at least there are hopes that at some point these devices will go from being experimental platforms to being theoretical computational platforms. Anyway, so this is real, well, real in the sense they just remotely on this machine, they run this also annealing protocol. This is some interacting Ising problem, so it's not NP-hard, but anyway, they did what they did. And essentially they sort of did the same thing, but now they implemented commutator expansion variational. And this is also fidelity they got. This is a theory mental plot. So these are not simulations on Apple computer. This is what IBM gave to them. So, and this is fidelity as a function of qubits. I honestly don't know what's the time scale there, but obviously pretty short because without CD, the fidelity just is very bad. And then they see that if you apply variational thing, again, they see substantial improvement. It never goes to 1. You have to add more and more commutators, or actually there are some other ideas around, but anyway, you get improvement. So another example is where I think we got like spectacular result is from original paper by Dries. This is like fighting Anderson orthogonality catastrophe. So it's almost like, as I said, we are throwing a stone without creating ripples. So mathematically, we have some Fermi C, non-interacting, but then we turn on some potential locally. So we turn it on. And then we know this is where Anderson orthogonality catastrophe tells us that adiabatic transitions are difficult. So now we do the same thing. We're just saying, well, this is our Hamiltonian. We want to find approximate gauge potential. It's imaginary, so it has to be a current. But in a full exact solution, it's non-local current. Even though the problem is non-interacting, it's difficult because we break translational symmetry. But variationally, we just say, let's apply local currents. And this could be translated to local potentials and local hoppings. And like with the waiter, I'm not going to there. So
this A is an ansatz, or is it something?
This A is ansatz. Yes, it's variational ansatz. And then if we do infinite temperature minimization, it's just, again, one line to get this equation. So this alpha should satisfy this equation, and these are discrete derivatives. We can take continuous limited, there will be continuous derivatives, right? So we just need to solve some Laplace equation. So if my potential is weak, I ignore this, and you see this is just my gradient of potential is a source term for my
V is the potential you add.
V is the potential I'm adding, right? So lambda is strength of the potential.
I see.
And then I have this extra term, which is grad V squared. I don't know exactly what the analogy is there, but maybe there are, like an electromagnetism, maybe one can think about analogies as well. So this is almost like a charge if I interpret this as electric field. Anyway, so we can do it. So this is roughly how it looks. So remember, lambda is the magnitude. So this is A lambda. It's my current magnitude. And this current is weak at the boundaries, that it increases, then goes down. As I said, you can convert it to potential and hopping. I just don't want to go there. So you don't really need to implement current in the lab. But then we got, like, I think still probably best results I saw ever. Well, Dries got this result, that if we look into fidelity, and this is non-interacting problem, but big, 500 sites, 256 particles, so half filling. And here it's a ground state. So we do infinite temperature optimization, right, at half filling. So we can fill the whole band, right? And then we apply them to ground state at half filling. And then fidelity, if we just T here is duration of the protocol. So if we do nothing, this is dashed line, at the end of the protocol, fidelity 10 to the minus 30. This is precisely the orthogonality catastrophe. It's impossible to be adiabatic. But now if we do this sort of this variational CD, which I briefly discussed, you actually go to many-body fidelity 0.5. So remember, first when we submitted this paper, referee said, well, 0.5, it's not impressive. But you have to understand, it's 0.5 for 256 particles. So it's 0.5 is exponent of minus 256 times fidelity per particle. So we get basically 99.99% per particle. It's actually very impressive. Now I'm moving.
What was this FF in this?
Oh, fast forward it's like with Waiter. When I do rotation, gauge transformation like with Waiter, and basically I convert this to this protocol to a protocol where I change only locally potential and hopping. And yeah, I think I skipped. Maybe I even have this slide. Okay. No, I didn't include it, but I can find it. So there is some shape when you have to turn it on, make it negative, turn it on. So all these protocols have actually interesting bucket type shape. So you overshoot and then you catch. It's like if you think about the bucket, we thought about this, how you want to move the bucket with water, like quickly, or squeeze the bucket. You actually first overshoot and then catch. So all protocols actually, even in quantum systems or whatever, they have this feature. And the same, like for example, harmonic potential. This is exact solution by Jarzynski. Imagine that you have harmonic potential and you want to say reduce spring constant, make it smaller. Actually, the way to do it in a fastest way, I didn't actually make a connection to speed limits, but these protocols, they actually saturate quantum speed limits when you have exact. Anyway, so the fastest way to do it is to first do inverse protocol. So make basically inverted parabola, then your wave packet or whatever starts spread quickly, and then you catch it. And it turns out that's the fastest thing you can ever do. And that's exactly counter-adiabatic. So yeah, the last part of this problem of this issue, I had a second question, which I mentioned, and which was basically solved by Peter. is that we can do, how we can realize it. And it turns out this Floquet theory comes to rescue. And there are many experts here, and I had the past lots of conversations with Shmuel Fishman about this. Yeah. Anyway, and the idea is very simple. So, I mean, there are, of course, many experts in Floquet theory, and Nathaniel included. Let me just have very short overview of why these things are relevant. So, I mean, Floquet can be, of course, arbitrary protocol, but let me just, for simplicity, draw a step protocol. So we basically half of the period or some fraction of the period we run with one Hamiltonian, then with another, and then we repeat, right? And then we can say that our unitary will be e to the minus what we call Floquet Hamiltonian. This is basically definition of Floquet. And then we can do some high short time expansion of this protocol. And what I want to highlight, it's a commutator expansion, right? But now let's stare a little bit on this ansatz, which works so successfully in many cases. It's also a commutator expansion. So now what we are facing, the problem we are facing, and the problem which Peter solved, is that which Floquet protocol realizes exactly this commutator expansion. And this solution he found is very simple. It's not unique, of course, but this is like as a matter of principle. And as a matter of principle, he proved that you can reproduce this protocol to any order. And there are like basically two ingredients. So first of all, because commutators, you need d lambda h and h, it means you don't need to introduce additional controls. So it basically means that you have your Hamiltonian, it's one control, and you have a conjugate to your annealing parameter, which is part of your Hamiltonian. That's another control. And these are the only terms you need to worry about. So if you can control them, you are done. And then what you need to do, you are shaking Hamiltonian in a particular way, and you are shaking at multiples of this frequency omega, your whatever generalized or conjugate to your lambda. And then these coefficients work in a way that if you do short time expansions, you have to shake at high frequency, only these commutators will survive. Everything else will disappear. They will be either of resonance or suppressed by high powers of omega.
Can you explain again what I mean? So this type of the form of this Floquet comes from the fact that your guess for a lambda, right?
Yes. So I want to find.
Can you explain again where this guess comes from? Yeah.
Well, this is, we know this is the answer for a lambda. Now we want to find Floquet protocol which only has these commutators, because generally you will have also like
I understand. Yeah.
Yeah, so you need to kill all other terms.
But this is not an exact. Is this a lambda an exact solution? No.
No, this is variational.
This is also variational.
If you add more and more terms, it will be more and more exact. For example, if you have single spin problem, this is exact. It gives you sigma y. If you have two spin problem, this is exact. If you have three spin problem, you have to add more commutators and so on. But if you have large system, you always, of course, need to stop your variation on that somewhere, and then it will be approximate solution. But say you found it variationally, and now you want to realize it in the lab, right? And then if you can realize this Floquet driving, then it will work. You can even see why it should work like this, because you see you have, say, d lambda h power 3 omega, and you need to use h 3 times in order in high frequency expansion to get this term and so on. So you know all these things. So there are no like surprises here. But this protocol has one subtlety, one caveat, and we still don't know how to solve it in general, that if you want to be arbitrary fast, so you want, of course, your driving frequency should be at least faster than duration of the protocol, then the scale is omega naught. So omega should be at least omega naught. Again, I'm not going into details, but you need to change sign of your Hamiltonian. When you do annealing, it's fine. But if you think about experimental setup, it's not fine. And again, this gives you speed limits. So basically, if you have annealing, if you don't have any bounds, so you can just have arbitrary amplitudes or whatever, this can be arbitrary fast. If you have real material, and we have some examples there, you are limited. So if you want to insist that this term is positive, it's not that this is impossible, but you are limited in how fast you can do things. No, I think
so the advantage in doing the Floquet, just to understand the Floquet counter-adiabatic driving, is that I don't need to act with an complicated operator with this commutator.
Yes, because this, exactly, because if you think about this, so I just mentioned there are actual examples and also spin examples where this second term gives you huge advantages. Not the first one, but the second one. Still, I don't have a good intuition why this happens, but there are more than one examples like that. In some examples, first term is enough, but in some examples, you really need to go second. Like, for example, if you have Ising model, if you want to turn on interactions, first term is almost useless. So you really have to use this term. Anyway, so, and if you take like any Hamiltonian, like I don't know, particle in a potential, spin system or whatever, this will be fairly complicated. I mean, when you compute 3 commutators, you'll get many different terms, so it looks ugly and so on. So if you want to realize this in a lab term by term, good luck. I mean, maybe it's possible, but it's difficult. But here, if you do Floquet, then actually your controls are harmonics, Fourier harmonics. So if you want to realize this protocol, you just need 2 Fourier harmonics, right? You have only 2 controls. And you don't need to introduce extra couplings also. So maybe I'll skip this. I'm close to the end. I just want maybe to say in words. So in lab of Alex Sushkov, I should say, Eric was the main student who was working on this, realized that in a lab for just an NV center, spin half system, so it's trivial, but they realized it in the presence of the noise, and it makes things much less trivial. So how you sort of do adiabatic evolution with noise, right? If you do it slowly, it won't work because noise will kill you. So you need to do it fast, and then counter-adiabatic helps. So basically, without explaining what this picture means, I will tell you that this Floquet counter-adiabatic turned out to be also very robust to the noise. So it's actually much better than normal counter-adiabatic protocol, at least in the lab. So maybe
some sort of dynamical decoupling to the noise.
Yes. Of course, it involves, but this is a combination of dynamical decoupling and counter-adiabatic. But yes, you're absolutely right. It's dynamical decoupling. So let me just maybe give you 2 slides of summary. So one, it's what I didn't tell you about, like other applications of these transformations, approximate transformations. But let me just say, because I think these are kind of interesting and so on. I was talking about particular sort of question how we suppress dissipation. But it turns out this AGP is also a generator of Schrieffer-Wolff transformations. So it's a way to get low energy Hamiltonian. If you think about this, that's exactly what we are doing. We adiabatically eliminate excited states, and that's exactly what I was doing. And then work where also Peter Kleis was involved and Jonathan Wurtz, who was a student, was leading it. We found that you can get extremely accurate effective Hamiltonians through variational Schrieffer-Wolff transformation, not perturbative variational. We use the same variational procedure. And you can describe quenches using this sort of a truncated Hilbert space approach. So where you usually throw out, say, excited states. But here you first do unitary rotation. So almost diagonalize Hamiltonian, or make it block diagonal, I should say. Remove excited states, do your evolution in truncated space, and come back. And you get much more accurate results than, like, orders of magnitude more accurate than if you just do truncation. Then this would be like another potential for the talk, is that through this adiabatic transformations, I said this actually generate AGP diverges in quantum chaotic systems, but it turns out that we realize that you can use it as your advantage, and you can probe chaos because it diverges. It's actually super sensitive. And one of these results, we are at least personally almost confident that there's sort of no many-body localization transition. So there were like so many mistakes in other papers, but this would be like a separate talk. So, and one thing we also found, and which was also missed, and it's non-trivial thing, but was completely missed in NBL literature, is that there is no direct transition from integrable to ergodic systems. So there is like a region of maximal chaos where we have maximal sensitivity of eigenstates. So basically integrability to chaos ergodicity transition is extremely interesting, extremely rich, and universal. But of course, I cannot say much about this. Then a work where involved another student, Miro and Anusha Chandran, my colleague. We actually used counter-diabatic to realize small heat engines, like have very quick isothermal processes. And it also worked amazingly well. It's again, simple system, but protocols are kind of non-trivial. And yeah, there are non-trivial, there's non-intuitive results, I should say. Another work which involved Sho Sugiura, who is now like MIT/Tokyo, also Peter Kleis, Toly Demarsky. We analyzed adiabatic landscapes, like what's the optimal adiabatic path. And we accidentally found that this is the way to look, like study adiabatic flows. If you have like two coupling space, you can actually sort of identify integral points, and you can identify dark states, or people call them scars. And we actually found what already people found new in very robust ways. So it turns out that these adiabatic flows are extremely singular near the points which sort of give rise to all these fragmented Hilbert spaces and so on. You can identify those things. And then same which we started working even before I started working in counter-diabatic, it's sort of geometry and topology of phases. So for example, if I define the metric as a variance of this gauge potential for my ground state manifold, I can map it to some geometry, and I can ask like how my phases, say quantum phases, can be represented through geometry. And it turns out, like, for example, transversal Ising model is represented through this shape. And there are universal topological geometrical numbers related to Euler characteristics, not to Berry curvature, which are completely characterizing these phases. And what to do with them, we don't know. But at least now there is a hope to study geometry of chaos, and that's what I know 2 students now in Moscow in School Tech are doing, and they're getting some interesting results. Or just find approximate geometries through this variational approach and so on. Yeah, I forgot to mention other things like connections to speed limits, Flokia, and so on. But it's really, once you start working on this, you realize you see these gauge potentials everywhere. So I want to summarize. So I discussed general variational approach to finding approximate AGPs, this generator of adiabatic transformations. Remember, it started from the problem, what is the canonical transformation which makes, I don't know, some quartic Hamiltonian time independent? And yeah, I just basically discussed some approaches for doing it. Not the only approaches, but it seems to work very well. Then one thing which actually also Nathaniel asked, and what is still like a huge surprise for me, that in many systems, like I mentioned, this Hubbard, or so fermion, not Hubbard, just free fermions on lattice, many spin systems, infinite temperature or classical, by the way, was studied a lot by Wierzyński, adiabatic gauge potential works extremely well for ground states. So it's like, to me, it's still surprising. So when we talk about these fermions, infinite temperature, this minimization, knows extremely well about how to keep ground state constant. And this even checks, so if we reduce filling factor, it still works amazingly well, even though, you know, ground state knows only about bottom of the band, while infinite temperature knows about everything. So there is much more information at infinite temperatures at ground state that we saw. Like in equilibrium statistical mechanics, infinite temperature knows nothing, its identity. But when we talk about dynamics, we actually know a lot. Then I discussed some possible ways of designing approximate protocols using this variational procedure for realization. And I went through some applications. So I think with this, I would like to thank everyone. And sorry for being a little bit over time.
Thank you very much. Okay, so let's see if there are any questions from the audience. I think I've asked many.
So, yeah, I have a question. So first of all, let me just super quickly see whether I understood correctly the general idea of the thing. So I like to think of the waiter picture, kind of picture, right? So that is that you want to move, say, the potential of the system and then compensate it with another mechanism in the Hamiltonian such that it doesn't fall. So in that example, the motion, the perturbation of the system is the waiter that is running. The system is the glasses on the thing, and the compensation is the tilting of the thing. Exactly. Okay, cool. So, but then the problem is that classically, apparently you can't do it exactly, and then you start looking at.
No, you cannot. No, you cannot. Only in special cases you can.
Right, right. And so you looked at this variational ansatz that essentially does an almost non-adiabatic. So you are tilting you're compensating the motion of the waiter, but you're not fully successful. So the glass still tilts a bit or something, right?
Yes.
Okay, cool. Yes. And then one thing is, so intuitively, I struggle to see why you should not be able to compensate the thing not to make the glass tilt. And the only way in which I can imagine that you fail to do so is that because there is no friction, and that's why like in a sense there is no dissipative dynamics, and that's why you fail to compensate it exactly. So I want to ask if this is the case, and if so, whether in the presence of friction you could actually lift these mathematical fine features of the classical limit that makes it not work, and so with friction you lift it, and actually you can find exact.
Yeah, it's a very interesting question, and actually some groups are working on this. Like in particular, the group of Saro Fazio, that they actually recently had a paper, and indirectly we also had this paper with Temiro. We are indirectly found an answer to a question, but a very particular setup, and also in Fazio. So we don't know how things change now. But what seems to happen is sort of the following. So if you have an open system, so here the system is actually closed, we analyzed, but we have sort of many oscillators which form the bass, and if you want, our system is like our probe oscillator couples to one of them. So it's a bass, but we don't make any approximations, Markovian or whatever, but it's Cadeler-legged bass, so it's perfectly fine and so on. And actually what we found is interesting. So if you are very slow, then of course you are reversible. Say, suppose you want to transfer temperature from here to here. You start in the ground state, you couple, and then you adiabatically expand the potential. You go through resonance, right? And when you go through resonance, you exchange energy. And that's actually perfect because you have many oscillators. This is a perfect thermal machine. So you can do whatever you want. So, and then you start doing things faster. And then actually what we found that using the protocol we developed, and Temiro developed protocol just for two oscillators, it's sufficiently complicated. So he didn't use even variational approach. He just found exact protocol for two and checked how it applies to many. And then what happens that for a while, this counter adiabatic is doing nothing, zero. So it means that sort of quality of transfer gets worse and worse if you go faster and faster. So if your quality or inequality increases, then counter adiabatic and non-counter adiabatic is the same. But then if you start doing things even faster, so faster than bus-bus interaction or faster than Markovian scale, counter adiabatic becomes super efficient, and equality actually starts going down. So without counter adiabatic, it gets up, well, in quality, and here it goes down. And I don't have plot with me, but it basically goes back from 0 to 10%, while in some units, while no counter adiabatic goes to 100%. So you get like huge improvement. So, and actually similar results were seen by Hartman and Lerner. I mentioned their result from the same paper for quantum annealing. Similar results were seen by Fazio. And it seems that the conclusion is sort of the following. So if I want to throw stone into the water without creating ripples, water does has dissipation. Of course, I can do it slowly, and then I don't need any counter adiabatic. I can do it at intermediate time scales. So basically time scales of the order of relaxation to the bass. And then I cannot do anything. Maybe there are some other protocols which work, but we couldn't find it, and other people, whatever they try, it doesn't work. Or you can do it quickly. When you are doing it quickly, of course, you excite a lot of energy, but it's not dissipated yet. You're excited in terms of big waves, and those are easy to fight with. You can create counter protocol which fights with big waves. So basically, the answer to your question is that it seems that if you do things faster than Markovian limit, you can be efficient. If you do slower than Markovian limit, it looks like you indeed dissipating things and you cannot do much.
Okay, thanks. And is Saro quantum or classical?
Saro was quantum.
Okay.
Yeah, they were doing quantum. Like
Okay.
they were solving Lindblad equations for some spin systems.
Yeah, I wonder whether your formalism can be generated with dissipation if you go just
Yes,
to...
yes, yes. They generalized formalism, but they found sort of same results that essentially you cannot really fight with dissipative part. So they found basically a variational approach with when you ignore dissipation and when you include dissipation, they give you basically identical result in the presence of dissipation. And whether it works or not depends on how strong dissipation is.
Okay, thanks.
Yerzynsky also worked like on master equation. So suppose you even don't have Hamiltonian dynamics, you have a master equation and you ask, what shall you do, for example, to follow Gibbs state? Like you have a same particle, it's coupled to say Markovian mass, right? And then you just want to change potential quickly, but such that you're always in Gibbs distribution. So he found a solution. So there is a solution, but this solution corresponds to super strong dissipation, actually. It's kind of achieves opposite, but it keeps the system always in the Gibbs state if you run quickly. So in this case, but in this case, at least Yerzynsky considered very specific setup, one-dimensional particle in some Gibbs distribution and so on. How these results could be generalized, I don't know.
Okay, thanks.
Other questions? So I can, in the meantime, I can ask something. So can you, I did not understand, or I was not supposed to understand the connection between this IGPs and the, this quantum chaos MBL question.
Mm-hmm.
So how did you? I mean, you somehow said that you can use these AGPs to
yeah, well,
study the question of.
So yeah, MBL will be like totally separate discussion. I even don't want to start it now, but yeah, this is how we came to sort of MBL, and then of course there was separate work in MBL. So there was like a work started by Mahit Pandey actually with these cells, like it lasted for years, but then he found, I would say accidentally, some spectacular results. So basically we thought, can you really see something interesting in this norm of metric which is basically norm of this AGP in chaotic systems, and when you go from, say, integrability to chaos. And to make long story short, it turns out that this sensitivity of eigenstates, basically I'm measuring sensitivity of eigenstates, right? This metric tensor tells you what is the magnitude of derivative of eigenstate with respect to parameter, how fast it changes, right? And then what he found is that this measure is like super sensitive to tiny chaos, much more sensitive than level statistics. By much, I mean orders of magnitude, and also it's exponential with system size. So it's like they have different scaling. So level statistics is much harder. Yeah. This is much weaker system size scaling. So it's a super sensitive probe of chaos, right? So, and then the other thing which we found there is kind of interesting, that in integrable systems, the scaling of AGP is always polynomial. So it basically means that integrable systems have...
Scaling of AGP, you mean you're looking at this AGP gauge potential?
Yes, yes, yes.
And you're looking at the norm or what?
So, yeah, norm, exactly. So it's the same norm I mentioned. So this is what's also known as Fubini study metric. And basically the conclusion that in integrable systems, this AGP is quasi-local operator. And basically it's kind of, I said, it has many symmetries. And this was actually not really surprising to people who do integrability. They maybe didn't know in this language, but they were not surprised. And this is not surprising because I guess what I didn't mention, that this norm divergence comes from small denominators, and finite norm means that the matrix element vanishes at small denominators, and you don't have problem with small denominators. So basically I can reformulate this. Integrable systems don't have problem with small denominators. And you could say, I know that, but anyway. ETH has this exponential scaling, e power s, which I briefly mentioned. But it turns out there is a regime between them where we have e power to s scaling. So basically, if you think about this susceptibility, this is color plot of this norm of fidelity susceptibility or metric tensor or norm of this AGP. It's actually is very small, then it becomes huge, e power to s, and then drops down to e power s. That's basically between ETH and integrable regimes, there is like a region of maximal chaos where you are most sensitive. And this is also related to like operator growth, like many other things. And yeah, then we just try to apply this to MBL, and we just reproduced Poisson results, but then we saw a drift, like it never stops. But then we actually did a little bit more work, found some local, this what they call LEOM, local integrals of motion. It's also done through AGP, essentially it's the same construction, and found that they're unstable. Actually, they're never exponential. So whatever people say is just incorrect. Anyway, but that's
so here the AGP is supposed to take you to what? To between what two Hamiltonians?
Well, it dresses the state. So, well, we looked into different examples. So in original one, we looked into, say, you start from XXZ model and add a magnetic field on one side, which breaks integrability, or add second nearest neighbor interactions, right? And then what you see that there are basically always two lines. Maybe they're crossovers, but they're extremely sharp. They're extremely well-defined. And you can sort of see it even in this sort of color plot. I mean, it's a cartoon, but it's taken, color plot is for actual system. So I guess system size here is like 14, it's not very big. So, and what happens that you have like a very sharp crossover from polynomial scaling of AGP norm with system size to e power to s scaling. So basically faster than ETH. And then you go through a maximum, and after that you quickly grow to ETH scaling. So in thermodynamic limit, at least well, I think in all systems, at least all we know, both lines go to zero. So in some sense, as you increase system size, but one goes to zero much faster than another. We still don't quite understand scale. So, and there are many issues with MBL, which also people slowly acknowledge now, that once you go to, this is what be MBL language localized regime, you will actually see that perturbation theory breaks down. Like it's super complicated regime, which is chaotic but non-ergodic. So there's always like a buffer which separates ergodic ETH from integral. And this was actually issue with RGs. In all RGs which predicted this MBL transition, they always assume there is direct transition. And it turns out, well, it just, once we understand, first of all, it's impossible, like mathematically impossible, unless there is some spectral gap or whatever. And second, if you revisit those RGs, you actually see that they see this chaos and it leads to divergences. So these RGs, at least I know, are just mathematically wrong. They just have mathematical mistakes because they made some assumptions and which exclude this.
You're saying this the maximal chaotic region is not ergodic somehow. It doesn't.
It's not ergodic, yes.
Satisfy ETH.
Yeah, so in MBL language, it's basically a regime when we have coexistence of localization. And
is it some sort of a Griffith phase or what? Or
well, I don't know. I mean, this phase exists even without disorder. So maybe you can say it's a Griffiths in energy space, in the sense that you have huge state-to-state fluctuations. So there are different eigenstates. They're kind of not yet. So if you want, these are states which are dominated by these rare resonances. So this language sort of developed in MBL literature. So, and in ETH regime, you don't have rare resonances. Each level collides with every other level, right? So this is language of rare resonances, which are extremely mobile. In the sense, you change the parameter, they move completely. And because of that, you actually eigenstates are like super sensitive. But at the same time, you still have signatures of localization. So in this region, in I would say cleaner systems, we got, I guess better interpretation of numerical data. But even there, we couldn't. So we did work actually with Marcos Rigo on this. We couldn't make sense of the results. So none of the scalings we tried work. So there is nothing perturbative in this region. So, and basically just to give you scales, if you have XXZ model, like largest without disorder they analyzed was 24 sites, but in, of course, symmetry sector and so on, it was million computer hours. So this is the largest size they can do. And then if you, so at these scales, you have ETH transition at say magnetic field on one impurity of the order of 10 to the minus 3. So it's fairly small number. It's like 3 times 10 to the minus 3.
That's a value for transition into ETH.
That's the value for this line, yeah. This line we didn't even identify because once you go to 10 to the minus 6 and 10 to the minus 7, perturbation theory doesn't work. So we have like many orders of magnitude. So it's huge regime. So both in some sense exponentially small, at least for clean models, but it's huge separation between them. And we don't know what's the proper language. I mean, people say resonances and so on, maybe, but so far we didn't see any, I don't know, mathematically, predictive theory which we could feed to Marcos data. So you can just say square root of, if you just study, I don't know, say spectral function, right? So Fourier transform, basically of diagonal matrix elements of your observables. You'll find a square root of U behavior and so on. If you go to larger interactions, you just see Fermi-Golden rule, you just see like what you're supposed to see, Lorentz and so on. Here, it's all different. It seems fairly universal, fairly robust, but we couldn't make sense what's going on. Need more analytics.
Interesting. Okay. Okay, so any other questions to Anatoly? Okay, so yeah, I think we can thank you for this very interesting seminar. And I told you, yeah, I'd be happy to hear more about this MBL stuff. It seems very interesting. I'm wondering, yeah, I mean, if it's
maybe in May,
yeah.
I'm thinking about this. I'll probably
people did discuss this super dissipative, not super, subdiffusive regime. But yes, this is not it. This is not the regime you're thinking about.
Well, no, yeah, it's all happening here. Yeah. So you have, I mean, you have to be a little bit careful because subdiffusive regime happens also here, but in frequency window. Right? Because in some sense, you just think if you take thermodynamic limit, this regime is say everywhere. But of course, there is subdiffusive regime, but it's finite frequency window. That's what we believe, and well, for some models we have certain. Right. So, but here it goes all the way to Heisenberg scale. So basically, all the way to level spacing, you have this interesting subdiffusive logarithmic. Actually, now there is like work. Anusha is working with. I also know like in Flokia systems, Tatsuhiko Ikeda and Shodex looked at this. It's extremely interesting regime. It almost looks like log in time, 1 over frequency spectral function. So it's like 1 over F noise if you want, but it's not exactly. It just keeps drifting. So we still don't know what's the correct functional form.
Of what? Functional form of what? Sorry.
It's spectral function. So the noise, right? So this regime is basically, I would say it's 1 over F noise regime, except that it's not quite.
It's not what?
There are deviations. It's not quite 1 over F.
I see.
So it's close to, but...
You're saying that the spectral function look like 1 over F noise.
Yeah, so it's definitely 1 over F squared is Fermi-Golden rule, right? It's Lorentz.
Yeah.
Constant is like what ETH, low frequency behavior. It's like you saturate, right? It's random matrix theory. Here it's slower. You have slow dynamics. So it's slower than, constant. Well, I don't know. I mean, it's between 1 over F squared and constant. And in some cases, it's very close to 1 over F. In some cases, it's not that close to 1 over F, but it always drifts. So like Anusha now suggests it could be stretched exponential in time or something, but it's not a simple power law behavior. So like subdiffusion, people say it's 1 over t power alpha. That's certainly inconsistent with numerics. It's yeah, and then, but other people also found it. So you cannot discuss this regime with some constant alpha.
Interesting. And when you're studying this with these AGPs, I mean, where do you actually compute the AGP? I mean, at what value of I mean, you're trying to tune between the integrable.
Well, yeah, it's a function of lambda. So in this paper with Tyler, we just looked into the whole regime.
So this is the value of lambda at that point, at the point.
Yes, exactly.
Interesting.
Well, I mean, here you fix lambda, but change system size. Well, lambda is, think about this axis vertical.
Yeah, the lambda is like the y-axis, right?
Yes.
And you compute this AGP at the lambda that you're trying to.
It's actually even more interesting. Once you break integrability, you have notion of parallel directions to integrability and orthogonal. So suppose lambda breaks integrability, right? Then you can still study metric along integrable direction, so AGP, and perpendicular. And there you have huge anisotropy as well. So basically you have to study two-dimensional manifold, and there is very interesting sort of geometry.
But you're trying to, I mean, you are trying to basically interpolate along the non-integrable direction, right? Between the integrable one.
We tried both. So qualitatively, it looks similar, but there are some important caveats, like how you go from this line, there is a big difference. So like, for example, this line is most visible when you probe along integrable direction, could be saying x-axis chain anisotropy, right? Anisotropy is the interaction keeps your model integrable all the time. So this is parallel to integrability relation. But we break our integrability by longitudinal field, right? So here, this would be metric along parallel to integrability direction, but this scale will be integrability breaking. But in the paper with Marcus, we studied both. So you also have like interesting, and this is more relevant to sort of this paper briefly, when you talk about landscapes near, well, I even didn't explain what it is, but there are two couplings here. But basically there are singular points where these are integrable, like special lines. And there you have huge anisotropy on flows. So, and yeah, there is like nice geometry, topology. We don't know what to do with that, but it looks beautiful.
Oh, very interesting. Okay. Yeah, so hope to see you in Israel in May, I guess, right? It's in May.
Yes, I hope to come as well.
Yeah. It's not too far in the future. Okay, thanks a lot. So sorry?
I just wanted to thank everyone for listening.
Yeah, it was great. So maybe we could, get you over again to tell us more stuff. You can be in touch.
Well, I'm always happy, of course.
And say hi to everybody at BU.
Sure, I will.
All right. Thanks a lot.
Bye.
Bye-bye.
Bye.